Welcome to Program of Physics and Astronomy. It's my great pleasure to introduce today's speaker, Professor Ping Yu from our long-term friend, University of Missouri, Columbia. Professor Yu obtained his bachelor's and master's degree from Nankai University, one of the premier universities in China. He then moved to Hong Kong and got his PhD from Hong Kong University of Science and Technology, and that's back in 1998. He then did a postdoc at Technical University of Denmark, and then was a postdoc at Purdue University before he joined the University of Missouri, Columbia in 2003, and now he's a full professor at Physics and Astronomy department over there in Columbia. Dr. Yu received a career award from NSF and has many publications with about more than 6,000 citations so far. Please join me to welcome Dr. Yu to talk about Airy beams and applications.
Okay, thanks, Hui, and I feel honored to give a talk about my research work. So this work I initiated about a year ago, and this is a new result come out from my laboratory. I try to explain the fundamental physics, and so therefore it's not too boring, it's too special direction. And then I will introduce two applications of this this special beam, and I will tell you what this beam looks like. So this is the content of my talk. So I will, first I will introduce Gaussian beam and Airy beam, and then to talk about how to create and measure the property of this Airy beam, and two applications, and finally the conclusion and future work. If you look at some optical device like a laser, and you have a confocal cavity, you have gain median, and more than 100%, 99.98 reflectivity back mirror, and you could have like a helium-neon laser, you have 98% of the reflectivity, so therefore you have leakage, you have light come out from this mirror. And you can observe the beam of this light is a Gaussian beam. And intensity profile is a Gaussian function. If you look at the shape of this Gaussian beam, this is a plane containing the optical axis, and you can see that the Gaussian beam can be described by this kind of lines as a beam age. And of course, you can use a lens to refocus the beam or to collimate the beam. Another situation is single mode fiber. Single mode fiber because the fiber only support single mode TEM00. It is a Gaussian function. Well, it is not exactly Gaussian, but it's very close to a Gaussian function. So therefore, you have Gaussian beam come out from those kind of systems. So what is a Gaussian beam? Basically, it is a wave equation from Maxwell equations. You can get this wave equation. And if you drop off the time dependence, you get Helmholtz equation, and you solve this equation. And according to the boundary conditions, you can have different solutions. For example, plane wave, spherical wave, or cylindrical wave. But you can also get Gaussian wave if you convert that equation to per-axial Helmholtz equation. So the solution of this equation with boundary conditions, you can get Gaussian distribution of the electric field. Well, we're more interested on the intensity. So if we look at the intensity, intensity is a square of the electric field. So here's the expression for the intensity. In addition to this I naught, and you have this size dependent distribution. Basically, there's a Gaussian function which is 2 times of this rho square. So with some definition, especially this W define the beam size, and the beam size at z equals 0, you have smaller beam size according to the definition of this W. So here's a simulation of the Gaussian beam. And the whole picture is the picture contain the optical axis, so the light just propagate along this direction. And the brightness of this color means that it is more strong intensity at this point. And you found that the Gaussian beam, in fact, is a beam with diffraction, which means that at far field, you have this Fraunhofer diffraction, so it just diverge quickly. And at the focus, and your wavefront is a plane wave, and then you have a spherical wave come out towards the infinity, that your center of this sphere will come from the negative infinity all the way towards this part. One of the applications of a Gaussian beam into medical imaging is a confocal microscope. The reason that you can use Gaussian beam for confocal microscope is that Gaussian beam can be focused into a small spot because the intensity is all the same phase. So there's no negative phase that destroys your beam. So you'll be able to focus beam into a small spot. And the resolution around the optical axis or axial resolution is defined by this term called the depth of field, DOF, which is proportional to the this W0 squared, which is the beam size at this point, divided by lambda. Well, this depth of field somehow is important in the confocal microscope, but it's a disadvantage in some kind of imaging. For example, the optical coherent tomography, we would like to have a larger depth of field to get a clear imaging along the axis. So I will come back this a little bit later. The reason I'm emphasize this point is that the Airy beam can improve DOF. So what is Airy beam? So let's read this sentence over here. Airy beam is not related to the Airy diffraction pattern. We know that in optics, it's quite famous that when you have a small aperture, you have a telescope, you have a microscope, and your eyes always circular aperture. So the diffraction pattern of this circular aperture is Airy pattern. And it's quite famous in optics, and we already understand all those Airy patterns. But the Airy beam is not related to this Airy pattern. It's totally different. Airy beam looks like this. So these two images over here is the lateral cross-section of the intensity distribution of this Airy beam. It has a very strong spot at the center. We call this a mean lobe. And then with this pattern extend to this direction or that direction, depending on the coordinate system. It could be 45 degrees, or it could be up and down, so it doesn't matter. So you have this Airy pattern, we call this side lobes. If you move the observation plane to away from the z equals 0, for example, z equals 10 millimeter, and you find that you still keep the same pattern, but the mean lobe moved to another location in this beam. So basically, if you look at this pattern with a plane containing the optical axis, you will find that this mean lobe just move away from the optical axis, and your side lobe just follow the mean lobe. Airy beam or Airy solution was first discovered in a Schrödinger equation about a particle in gravity. So the first paper, 1979, discussed about the equation, this Schrödinger equation, and the solution is Airy function just like this. In the year of 2007, a group from Central Florida, they experimentally observed this Airy beam. And you found that Airy beam is different from Gaussian beam is that the mean lobe will not be diffract, will keep the shape for a longer distance. So this is something quite unique about the Airy beam. Before we further discuss the property of the Airy beam, so let's look at how to create an Airy beam. Suppose you have an Airy function. That is a two-dimensional Airy function described by this function. So we have AI means Airy, and another Airy function along the x and the y direction. My unit over here is a reduced unit. So you can see x and the y is converted into this mu and nu, and z is converted to this s. So if you have this Airy function, two-dimensional Airy function, and you perform a Fourier transform, and you'll be able to get a function like this. It is cubic proportional to this I, which means imaginary. It is power of 3 of this kx and ky. This is a Fourier transform of this Airy function. We know that in optics, if you have lens, and if you put an image in an object in the front focal point of the lens, or focal plane of the lens, and then you look at the back focal plane, and those two planes are Fourier transformed to each other. So basically, you can achieve this Airy function if you put this kind of a modulation, spatial modulation, at the front focal plane of a lens. So you have this phase modulation, and here is your Airy function. Now the phase modulation, it is in imaginary part. So this is just a decay factor. It is the imaginary part of this k power of 3, means that this is a cubic phase. So if we convert this phase into intensity, you will have the intensity modulation from dark to the bright, which means 2 pi phase difference, and then back to dark to bright. So basically, your phase modulation will be 0 to 2 pi to 4 pi to 6 pi to 8 pi. So you have this step phase from the bright, dark, bright, dark, bright, dark. So this is your phase modulation. If you'll be able to achieve this phase modulation, you'll be able to get Airy beam at the back focal plane of the lens. So this is how to create an Airy beam. And experimentally, you can achieve an Airy beam by using a device called spatial light modulator. So this is the commercial product SLM. So if you put SLM into the focal plane of the lens and the back focal plane, you will be able to get an Airy beam. And incoming light beam splitter and get a reflection, because those SLM is a reflection SLM. And you have phase modulation, the qubit phase modulation from 0 to all the way to 8 pi or 10 pi. And then they get a better focal plane, you have Airy beam over here. Depending on the modulation, you can get a different kind of shape. Now, this is the image contain the optical axis. Right now, the optical axis point up. So you can see this mean lobe just bend like this, bend like this, or bend like this, or even you can have something this kind of shape. And it's quite funny. And although people can get more and more kind of those special beam, but still try to identify what kind of application could be. Well, yes.
So you buy this whole line modulator.
Yes.
And it gives you an arbitrary spatial pattern of phase.
Right.
You can arbitrarily adjust the phase across a two-dimensional area.
It's called two-dimensional area, but it's not arbitrary. It should be a phase pattern according to this pattern.
That's what you want, yeah, but if you buy this device, you can do anything you want. That's my question. So you buy this thing and then you type in this phase and you get the area.
Right.
How does it work? How does the device work?
the device is based on the liquid crystal technology that you change the
So just little pixels of liquid crystals. that
yes,
you
adjust the phase shift from the single pixel.
Wow.
Yeah.
How much does it cost?
$10,000.
Good. I told you. But I go buy those.
Well, let me show you.
You need a lab too, right?
No. I will tell you a very low price solution about this.
Okay.
Oh, I have two solutions, and I will show you that there's fantastic solution. Okay, and now you need to get a phase modulation of this. So one of my understanding of this problem is that some questions people are asking. So you see Airy beam, and this part is totally dark, and your beam is just come out this part, okay? And the mean lobe of this beam bent towards this direction. In fact, it can be described as an acceleration of this mean lobe, just like acceleration of a particle in gravity.
You're bending light.
Yes.
In free space.
In free space.
Wow.
And totally dark. So how to understand the totally dark? My understanding of this is due to the phase cancellation. So all the phases in this dark part is just canceled each other. And the bright part is just described by Airy function, according to the equation over here. Okay, there's one problem, and this is quite a serious problem, is that if you do the integration of this Airy function, you'll get infinity. Basically, the power, the energy is infinity. But this is not true. This is not true in practice. And the way that we can solve this, or we can explain this phenomena, is that we can think about you have no infinity plane wave. You have only the wave you can get is Gaussian wave, close to the plane wave, but decay at the beam size. The energy just disappear outside beam size, a very small number of outside beam size. So basically, if you have a decay factor in the Airy beam, you perform the Fourier transform, and you will be able to get the qubit phase modulation plus something related to the Gaussian beam. So basically, your Gaussian beam limited the power, and your total energy of your beam will be a factor defined by this decay factor, which is smaller than 1. So basically, we are in a finite Airy beam, not infinity Airy beam. That is impossible in practice. Okay, now here comes the question. So how to create Airy beam? At the very beginning, when I talked with the people, tried to find out the solution, and they told me that you need to buy SLM. And at that time, I have no money to spend $10,000 to buy this expensive phase modulator. But you know, I'm physicist. I understand what's going on for the light beam. So I just want to do the phase modulation. So what means phase modulation? It's a phase grating. You modulate the phase in the plane wave or in the Gaussian wave. So how can I do this? We already have this device, Fresnel prism, Fresnel lens, that you change the thickness of a glass. And different thickness means that you have a different length of optical paths. You change the phase at that location. This is phase modulator. So basically, you can create a phase modulator by using photolithography or by using 3D printing. You just make a pattern in a piece of glass that with a different thickness. That is phase modulator because of different optical paths. So the idea of the Fresnel lens can be exactly applied here. Of course, Fresnel lens is a concentric circle that with a defined pattern. But over here, you need to have a pattern according to this image with different thickness. It is a phase grating. Basically, if you look at this, we call this a phase mask. If you look at this phase mask, you see nothing. because it just changes phase, not intensity. However, it will change the phase in the optical beam when you have plane wave. This solution is quite unique. You just need to define your wavelengths, what wavelengths you want to, and find out materials for this photosensitive, photoresistance layer, and then just make a pattern. Or you can use photolithography. People are doing Airy beam, electron beam for the Airy for the phase modulation to create Airy beam. And they just use a photolithography to make a very small pattern and to modulate the phase, because electron is a smaller particle compared to light wave. So this is something, you see that we can create a different phase pattern. So therefore, the Gaussian beam compared to the phase pattern, this decay factor will be different. We'll find that this is, in fact, is important for our application. Okay, now let's look at the, this is some kind of a basic of Airy beam, and we introduced a little bit with a Gaussian beam. So let's look at the one application that is, it is called the OCT, called Optical Coherent Tomography. The principle of this is fairly simple. You have low coherent light source. This is a SLED, which is a broadband light source. And you can also use a femtosecond laser. It's more expensive. SLED, a lower price semiconductor technology. This is high gain, single pass broadband light source with very good spatial coherence, good shape of light come out from there. And then you have a microscopy interferometer, just two beam interference, and reference and then signal. And you get those things back, reflection from the reference from the signal. And you see that we can control the polarization by using fiber polarizer. So when you have a polarization beam splitter, your back reflection will go to this channel, will not go back to the source. When you go to this channel, build up a spectrometer, you look at the spectral interference. Fourier transform spectral interference just gives the depth information. Well, I will not go details with this technology. Let me tell you a basic factor. I have been in this field for more than 15 years. And right now, the OCT technology is already used in clinics. If you go to eye clinics, any kind of small eye clinics, they have this OCT machine to look at the structure of retina, three-dimensional structure of retina. So basically, physics is very simple, microscopy interferometer. But engineering is quite complicated because you need to synchronize with the scanning beam and frame rate and all things together is a little bit complicated. Okay. Now we will look at something different. So we put a phase mask here. We will convert the light come out from this single mode fiber as a Gaussian beam. We will convert this Gaussian beam into Airy beam. Now, this is just computational work. The reason I show it here is that we have a smart way to do a high-speed imaging. The smart way is to use computer technology called GPU, graphic processing unit. And it is a technology because we need to do a lot of data processing with a Fourier transform, with image reconstruction, and all those kind of things. So it's fairly time-consuming. So we use GPU technology. GPU technology will decompose all of those complicated mathematical algorithm like Fourier transform, all those kinds of things, into simple work like plus and minus. So basically, you have a PhD student to do the single work for a long time. Now you have just elementary student to do a plus and minus, but a lot of students do it together. So basically, you have to decompose into multiple channels. So this is basically GPU works. It's very simple. You can get this kind of things from the graphic processor in your computer. $100, so we just do some work. And the reason that I am doing this is that I would like to look at small animal like a mouse. We know that a mouse just doesn't like human. It heartbeat is quick, 160 or 180 compared to 60 to 80 cycles per minute. It's very fast, and then the breath is fast. So you can see that we will be able to track the movement of a mouse skin. And this is the image. This is a cross-sectional image. You can see the blood vessels and all those kind of things. Now here's a differentiation. This is a wavelength-dependent differentiation. We're able to tell there's a cancer cells, cancer tumors at this location, cross-section, and this is the prostate cancer tissue that we were able to compare this into with the histology that we cut the tissue out. You can see the similarity of this. So all those things tells us that we are in the correct direction of the technology. Now, before we can use this Airy beam in the OCT technology, we need to answer some questions because we are working on broadband with different wavelengths. So we need to tell with the wavelength difference, you still get the same Airy beam or not. Now here's the calculation. I will not go detail, the Fresnel diffraction, wavelength dependence curvature, and then we also look at the wavelength dependence of this face mask, and then we did the simulation, and we did the experiment. So you can see the Airy beam difference is fairly small, barely see any kind of intensity. So this is a cross-section, lateral cross-section. This is a cross-section containing the optical axis. You can see the band of the mean lobe. Well, this Airy beam, as we said, it's not extend to the infinity because it's a finite size. So it just extends to some location beyond the extension, the depth of field of a Gaussian beam. Okay, and this is simulation experiment also showed a similar result. And here's we put this position of the face mask at a position away from the Fourier plane. We'll still be able to get the correct shape of the Airy beam. And this is a study to look at the decay factor with different face mask compared with different Gaussian beam. And we look at how decay factor acting on this mean lobe. So when we have a larger decay factor, you see that the Airy beam not extend as long as with a smaller decay factor. However, the sensor difference is from the side lobe. And we know that when you do the image, when you use this mean lobe as a single pixel, and this side lobe, in fact, gave a background noise. And we found that with larger decay factor, in fact, the side lobe is less important compared to the smaller decay factor. To the left is Gaussian beam for the comparison. And we calculate the intensity of this light with dB scale. And you found that all those background noise is about more than 20 dB below the signal. And this is quite significant because 20 dB is the detection limit of current technology of OCT. Basically, those side lobe will get less important for our image. And this is the result for the turbid median. We just put a polystyrene beads with different size into distal water, and we use the imaging technology to see different depths and to make a comparison of the Gaussian beam and the Airy beam. Now here is the result. You see that this is a Gaussian beam with the diffraction expand quickly. So this due to the diffraction of the light. And when you have Airy beam, if you look at the mean lobe, we already said that the side lobe is less important because it's just 20 dB below the signal. And we look at the mean lobe, and we found that for the Gaussian beam, the single spot converted into a line because the beam size is larger, where intensity decreases quickly and your intensity decreases quickly too. However, for the Airy beam, for all those panels just shows a small spot, which means that over here it still keep the same resolution. In another word, it extends depth of field. So here's another example. This is a biology tissue. This is from the onion tissue, and you can see for Gaussian beam it just decrease quickly, but for Airy beam, even with 5 millimeters, you still keep the shape of this onion. And the comparison for the Gaussian beam is that the Gaussian beam, the depth of field in this case is just 1 millimeter. The Airy beam, you can all the way to the 5 millimeter. You need to count to double side. So basically, you have 10 millimeters clear image field of view. That is significant improvement of depth of field by using Airy beam compared to the Gaussian beam. Okay, it's quite the initial study, and we just have an initial public paper submitted based on this work. Now, we just said that to create Airy beam, you need to get the phase modulation. So we can use Fresnel phase grating technology to make this phase modulation pattern. We can also use $0 technology. And this is from the projector. So our department has all the projectors would like to surplus. Just threw away, okay? I got 3 from the department, okay? And then we discharged this projector. We took out this LCD panel. So what is LCD panel? It is a liquid crystal. Inside this LCD panel, we have electrode control the orientation of the liquid crystal molecule orientation. And basically, you have intensity modulation, not phase modulation. That is because you have 2 polarizers below and above the liquid crystal panel. So if you throw away these 2 polarizers, you convert intensity modulation into phase modulation. This is a phase modulator, $0. It is not 2 pi phase modulator, it's a pi divided by 2. And then we need to have some polarizers. We need to 1 polarizer, 1 quarter wave plate, 1 half wave plate to convert each pixel of the pi over 2 into 2 pi. That is pretty simple. It's very easy. And so you see the twist of crystals. So when you have the polarizer, we just threw away these 2 polarizers. We convert the phase modulation. And we can build a double slit experiment to confirm that we have this phase modulation from the each pixel. Now remember, your projector, right now you have this screen, you have this projector. Whatever you have on your computer screen, it will copy to the projector. So basically, I just need to put my phase modulation pattern on the computer screen. So I found the desktop with 2 screens. So one is for the control data acquisition and other things. And another screen is just for display. And we know that the computer Windows just has a pretty simple way that you can display both screens simultaneously. So if I put the pattern, phase pattern in one screen, intensity modulation, and because I threw away this polarizer, the liquid crystal just provide a phase modulation, which is spatial light modulator. It's not the efficiency. The efficiency is not as high as a commercial SLM, but it works. It works in our case. So you see, this is the experimental setup. We have this projector control unit. We have 2 screens behind this board, and the LCD panel is here. We already threw away the cross polarizer, but we have to do something. We know that commercially available projector has a lot of sensors. It will tell you that if your light died, if your fans just dysfunction, and then it will stop working. And what we need to do is that we need to do something, treat the projector to tell that, oh, everything's okay. For example, when we remove the light bulb, we just put a resistor up there. And then we remove the fan, we put another resistor over there. And there's another sensor for the cover, so we just put something that press that sensor. So everything works. Just tell us that everything's okay, everything's work. And on the screen, we display this phase modulator. So you see here's the argon ion laser, here's the helium neon laser, this is a liquid crystal, and this is a half-wave plate, behind is a quarter-wave plate, and then there's another polarizer. So basically, this is spatial light modulator. What is the benefit of this kind of spatial modulator? Also, it is a lower price, it's $0. The benefit is that we can build a program to convert Airy beam and the Gaussian beam quickly, back and forth quickly. So this is the experimental setup. This is the experimental setup. We have laser and spatial light filter. So this is just a pinhole and a short focal length. And then this half-wave plate, quarter-wave plate, and polarizer. And this is a lens that convert phase modulation into Airy beam over here. And then we put a sample at this location. So you see that this is Airy beam and this is Gaussian beam. Basically, computer can convert these two screens quickly in the speed of this projector is 60 hertz. So every 30 hertz, 1 divided by 30 of a second, we can switch the beam from one another. If you look at the scattering, you want to compare the scattering of Gaussian beam and Airy beam, and this is a good way. This is a way that very similar to lock-in technology. You just lock to that one, and then your detection come out with a speckle pattern. So you look at this speckle, you measure the size of speckle because each image just corresponds to each beam in high speed. So you do not need to care about the Brownian motion, about any kind of other change in the system. But you can get data from there. Okay. Well, I do have a slide to show that at least in 10 centimeters, you still have a good Airy beam. Away from that, just a distortion. This is normal. And here's a result. And this is quite the initial result. I have an undergraduate student. He worked hard on this. I got this quickly result that to compare the horizontal axis is MFP. Basically, it is a parameter to tell how scattering density of your polystyrene beads or your turbulent medium could be. And to here is just without the scattering. And this is a highly scattering. In fact, we are in a two regime. This is what we call the single scattering event that coherent photons still be able to be detected in the system. So this is a regime of OCT. And this is highly scattered, diffusing scattering. And this is the light photon just bounce back and forth, totally lost the coherence. And we found that when we measure the speckle size between the Airy and the Gaussian, in the case of a highly scattering medium, they're almost identical. But in the case of lower coherence, when you'll be able to pick up a coherent photon, the speckle size is totally different. So we calculate the speckle size according to this equation. One potential explanation is due to the self-healing effect. Airy beam is a very special beam. If you have any kind of a defect inside that beam, the beam itself can recover by the beam itself. Now, for example, we have a block to block the mean lobe. and you still have this side lobe. And you see from here to here, and those side lobe try to recover the mean lobe, means that we move away from the focal point. The reason we have different intensity is not due to the intensity change of the beam. We know that the Airy beam intensity, shape and intensity keep the same. It is a diffraction-free beam. The reason we have different intensity is just because we would like to look at a special location. We have to build another imaging system, and that imaging system changes intensity. So basically, and this intensity and this intensity are identical. But Airy beam has a probability to recover itself. And then we measure the intensity as a function of distance. We have this slope due to the imaging problem, but we found that at a certain distance, the beam can recover by itself. And this recovering, it's different if we partially block the beam. For example, this is 80% of the mean lobe covered. This is 20% of mean lobe covered. So basically, at different location, this beam just recovered itself at a specific location. So what is the significance of this? It means that for the Airy beam, although it is scattered by cell by this heterogeneous inside turbulent medium, but the beam will try to recover itself, which means that the speckle size should be smaller because it's not just totally scattering, just try to recover itself. So this is a potential explanation, the reason that we'll be able to see the difference between the Airy beam and the Gaussian beam. However, the further study is still going on and try to fully understand how those self-healing effect, the impact on the scattering property of this Airy beam. Okay, here comes my conclusion, and we try to understand the basic physics of Airy beam, and we use two ways to create Airy beam for two applications. One is OCT, another is scattering of the turbulent medium by using this beam. There are a lot of questions. For example, the future work, we would like to develop a good phase mask and solve the phase cancellation problem, or apply ultra-high resolution OCT with Airy beam of other applications. I'd like to explain this a little bit more. OCT technology currently is beautifully used for the tissue imaging with current resolution. So if you compare current technology by Gaussian beam and Airy beam, there's not too much advantage, although the Airy beam improved depth of field. But after 2 or 3 millimeters, this coherent photon just lost the coherence. Basically, you cannot see anything deeper inside that. However, your coherent photon can survive with 2 or 3 photon, 3 millimeters. When you have an ultra-high resolution, in that case, Gaussian beam expands quickly. Airy beam does not. And it's to be able to get 2 or 3 millimeter depth penetration. So ultra-high resolution OCT is a direction to use Airy beam to get benefit from it. So this is my current calculation. I would like to thank my students and the collaborators and the people who provide face mask. Questions?
Questions? Yes.
Okay, so it's obvious you can use a video game. You don't need a projector, right?
Yes.
$10 video game.
Even computer screen is also, and the TV, LCD TV is also.
You can't buy them quick because they're going out of fashion, getting obsolete. They're replaced by LEDs.
Yeah.
Right? Now, here's my question. The Airy solution is borrowed from this Airy function quantum mechanics.
Yes.
Okay. It formally provides this increased depth of field and this localization of the beam, which is lovely. then you ended by saying that you have further technological issues, which amount to trying to know how to adjust the phase. Right? Now, since you've got computer-controlled phase, why can't you just do that stochastically by simulation? Why can't you write a Monte Carlo which will randomly adjust phases all over the computer screen, all over the transmission screen, and you look downstream in your turbid medium or in your optical observables, and you optimize what you're trying to do.
Yeah,
It's a high-dimensional optimization problem where you don't know the phase, but you know you're close to the phase because the area gives you something close to where you are. And you just adjust your way to that.
My answer to this question is threefold. First is this is a good question. The second is that I'm not familiar with this kind of simulation, but I can do this and take more time.
High-energy experimentalists can help you do that.
Yeah,
But you've got this output.
Yes. I need to find somebody who's familiar with the theory and simulation to do this kind of work. And my the third answer of this question is that this is totally new, that we are the first work to do this kind of things, which means that it's coming out. If I publish this result, there may be some groups who would like to do this kind of direction. I can imagine this.
Any other questions?
So can you apply the similar strategy to expand the wavelengths to say infrared or some other wavelengths like terahertz?
And
So the fabrication will be easier, right? You think
there are a lot of work right now in visible, and our wavelength range is in near infrared. And I also saw a paper in X-ray. So people try to find out potential applications for different wavelengths. And visible, I think longer wavelengths will be easier for the manufacturing because you do not need to solve a higher accuracy to get this phase modulation in lithography. The short wavelengths will be hard, but visible, I think right now the visible technology is already mature to get this phase modulation. There are many possibilities. For example, people ask me if you can modulate the phase in high intensity laser. Because when you make this kind of phase mask by using photolithography, normally it's soft material. You cannot, the device cannot stand for high power laser. And liquid crystal and commercial SLM device, they cannot stand for high power. So to get high power phase mask, you have to use a glass and make a pattern on that glass. And there's a company from Israel. They are trying to do this kind of things. And we know that light technology, in addition to low intensity light in bioimaging, you also have a strong light. So for strong light, if you want to do the phase modulation, you have to have a special device, phase mask for that. Which means that you can extend all directions, short pulses, strong light, different wavelengths, so all possibilities.
I have a follow-up question on that. We know that for Gaussian beam, the resolution power is inverse proportional to the wavelength. That's why we try to use short wavelengths for imaging purposes. How this Airy beam, the resolution goes with the wavelengths? Is that the same or?
I don't know. I don't know. It's a good question.
And also, I am trying to just try to understand this. You have this pattern with different loops and
side loops.
Yeah. What are their phase relation between the?
It's identical to the mean law.
So they are off by 2 pi basically.
No. It's the after modulation. They are the same phase.
Okay.
Yeah.
showed how it maintained this lobe for a certain distance.
Yes.
Is there what controls how far you can maintain?
It controlled by the decay factor. Means that your phase pattern, your well-defined phase pattern, and that pattern comparable to the Gaussian beam diameter. So you have larger diameter, you have smaller decay factor, and you can have this beam extend a longer distance. Have smaller Gaussian beam diameter, you just extend short distance. However, short distance, the side lobe is also decrease quickly, which is good for biomedical imaging.
Okay, any other questions? If that's not the case, let's start sign our speaker again.